Okay, let's get started. Thanks for joining. I'll share my screen. Okay, so today what we're going to learn are a couple of kind of novel uses of the mini AI framework, and it shows that the framework can be used to do not just the traditional learning algorithms of supervised learning, but it can also be used for different tasks which possibly it wasn't designed for from the start. But a couple of examples that not Jeremy, but John demonstrates in these two notebooks that we'll go through, or one is an application called Style Transfer, which, by the way, Jeremy has covered in an earlier version of the course that I'll point to as we go along as well. That's even more detailed, and it's also an interesting application that you can, similar discussion, but probably with different subtleties and using the fast AI framework, but you can port the same application and try to do it with mini AI as well. So that's kind of the context. What we're trying to do in essence is apply the style of one image to the second image that we provide as a reference. So let's look at examples of style transfer, or things like this, where you can see that the style of Van Gogh is being transferred to the application, to a Mona Lisa painting. There are, this Starry Night applied to the style of the Starry Night applied to this picture of houses. So you can see the result here, things of that nature. So, and you can see there's a picture of the astronomer, and here, this is a painting style, and then the style has been transferred onto his picture, so you can see the result here. So similar kind of, this is the screen transferred to the in a natural scene, and you can see the mountains with those colors and in that particular style. So that's what we are going for: how to take a image, how to take a reference style and apply the style to the image to get the result, and using mini AI. So what we do is we capture an image, and in fact, I've stuck to in these notebooks the same images that are used by Jono, but I would encourage each of you to try your own version of using both the reference images as well as the style images. So we download the image, and then this is the image that we want to transfer. The image that we want the style applied to is called the content image. So that's kind of the image that we print out initially, and that's, at least for this notebook, is the image of this lady in kind of like a fashionable style, and you can see the image here. What we do next is just check that, and in fact, the other thing we did discuss is the fact that you can actually directly use the Dot Vision IOD code instead of converting to Pillow, which is the Python image library. You can directly use Dot Vision and make it into a tensor, and the division by 255 is there to normalize the image. And it's actually done just to scale the image, I should say, not normalize, which we'll do in a minute. And then we download the image and kind of display it using show image that we've discussed previously. And then we check the bounds of the values. So you can see that the pixel values are between 0 and 1. content image max and min, so the values are between 0 and 1. So the goal, as I've stated before, is to transform style. But we'll start with a simpler exercise. What we'll first do is we'll take an image which is purely noise, and over a sequence of steps, we'll make it match the content image, such as this one that we provide, using a mean square error loss. So while the overall goal is to transfer a style from a reference image onto the content image, we start with a simpler goal or a simpler first step, which is just to make an image that we create ourselves starting from noise that would match the content image, right? So that's kind of what we set out to do initially. So we don't have training examples in this application, right? We just are modifying the noise into the content image. So what we do is to fit into kind of the mini AI framework, we need a data set, but we don't really have a data set. We just have a single image. It's not like we have a batch of images that we are trying to optimize and stuff. So we create kind of this dummy data set called the length data set, where we just say the option is provide is length of 1, so self.length is length. We return with len the self.length, and a get item, since we don't really care about the image, we are going to provide the image ourselves. So we just return a fixed tuple of 0, 0. And so get dummy data loaders essentially returns the data loader of length data set of length, and it's a batch size of 1. That's the training data loader, and the same thing we do for the validation data loader as well. So this is done just so that we can supply a single image and still fit into the mini AI framework, because it will expect data loaders. Right now, we write a tensor model class, which, as we've seen, is a subclass from nn.module of PyTorch, to which we pass the value t. And what we do is we reshape so we pass in an image shape thing, so right, that we can then optimize using the nn.parameter. So whatever we pass in, which is the image shaped thing to tensor model, we clone it, that is, we create a copy of it, and then we make the parameter. So we make that the parameter. So what we are doing by this step, where we say self.t is nn.parameter, is we are converting the pixels of the image itself, or whatever we pass in, which is image shaped, to be optimized by our optimizer. So typically, if you recall, we optimize the parameters of a model that we pass in. In this case, what we are trying to do, since we are trying to make pixels of image shaped thing into pixels that resemble the image or that display the image, we are actually optimizing the pixels itself. So in a sense, you can think of the model as being the pixels. So that's why we convert the pixels. So T is something that's image shaped. We convert that, we copy that, and we convert that into parameter. And then using the forward function of the model, this typically gets the X, which is the input. But in this case, we just ignore the X and in fact optimize, if you will, the parameters of the image shaping that we provide in to the tensor model. And that is self.t. So that's what we have initialized here, converted into parameters so that our optimization function can optimize these, and then we return that value. So this tensor model basically converts the image shape thing that we provide into parameters and then returns the value in our forward function so that the optimizer can optimize it as parameters. So this is optimizing the pixels as parameters, right? So then we create a model with the tensor model, and what we provide to the input is something that's random but in the shape of the content image. So because it's random, what you will see when we show the image is you'll see just noise. So this is just noise input, but now all the values of the pixels have become parameters to our model. And so if we check model.t.requires_grad, which means that all these pixels, because they're being converted to parameters, have become capable of being taken the gradient off. So that's what this says. And if we see the size of the shape of the parameters, it's exactly the shape of our image, right? So that's obtained by doing torch rand like the content image, which means it will produce 3 by 256 by 256 random values. So it's in the shape of the content image, and it's something that can be optimized. So then we defined image opt callback, since in the mini AI framework, we'd like to do things using callback.
What is model.t.requires_grad?
It just is an indication that the input that we have provided is something that can be taken gradients off. So this indicates what we're trying, as I showed you, this is something which ensures that the t that we pass in, the self.t that gets stored, is converted to parameters. So that this is just an illustration that because it's being converted to parameters, the t value, which is of the shape of the image and is stored in the model, has the required grad attribute set to true. So this is just a printing of model.t.requires_grad to indicate that the parameters are the pixels and they have this required grad attribute set, so that when we optimize, we can change these pixel values. Are you following?
Yeah.
And then this just shows that our parameters have the same shape as the image, which is to be expected, right? Because that's what we did here. We put the image, which is nothing but or image shape thing that we are providing to the model, stored it as the parameters of the model, and returned that in the forward part of our function. So when we create a tensor model and pass it a rand-like content image, that means we are passing it this image, which is exactly in the shape of our content image. It doesn't have the content image pixel, and the pixels are worthy, or they become capable of being optimized, which is what this particular instruction illustrates to us. So in the reference notebook, this is not printed. I just wanted to explicitly show you that the values of the required grad attribute for the pixels are set to true, and the parameter shape is exactly that of the content image. Then we create a callback where we add these two functions. The predict function just says, give me the model. And because that's the model now, will return in the forward the optimized values of the parameters, which will be as these pixels change, the model will give us the changed value of the pixels. That's simply what we're trying to do. And the loss is something where we just say that it's just the learn.preds. So whatever we are predicting is what we want the loss to be, right? The loss function actually just takes a single value. There is no labels to compare to. We are just giving it a single value, optimizing it using stochastic gradient return, and returning that value. We are not comparing whatever we are sending into the model with some label to see is there any difference. We're just returning whatever we are predicting, which is the optimized values of the pixels themselves. And that's what is done in the prediction function. And get loss just says we apply the loss function to just the predictions, right? So let's run that. And then the loss function itself that we apply to the pixels that are returned after every optimization step that we take is just the MSE loss between the content image, right, and our chosen input image. So in this case, as I said, we are taking a simpler first step. We are not going after the bigger objective we have. The bigger objective is convert the style image or apply the style image to the content image. That's not what we are doing here. All that we are trying to do here initially is go from noise to a content image, the noise which is shaped like the content image, and make that resemble the content image. How we do that? We do that by optimizing the pixels which are initially noise and making them take or take a number of optimization steps and change the pixel values to make them resemble the content image using an MSE loss function. So in effect, we are saying take these pixels with each optimization step, change these pixel values to resemble the pixels of the content image using the MSE loss between this image as after each step as it is optimized and the pixel values of the content image. Okay, so that's the action that we're taking. And the loss function MSE is just the MSE loss between whatever input we provide at each step after the optimization step, which is this IM, and the content image, which is the lady with the glasses that we saw earlier. And then, so we define this, the loss function, and then the model function is the tensor model that we have defined earlier. The callbacks we apply are the image of callback that gives us the predictions and the get loss function, the progress callback, the metrics callback, and the device callback. These are standard callbacks that we have already defined previously. And then we do the learner with the model, and we take dummy data loaders of 100. This get dummy data loaders is created in order to use the data loader function that we need for the learner. We apply the MSE loss function, the learning rate of 1 in x2, callbacks, and the optimizer we use is the same standard torch.optim that. If we do that, right, so we have just run this, and then if we display the result of the optimization, what we get is these images. So the left image is the target image, the result image, and the right image is the target image. So that means this is the original image that we provided, and this is the result of the optimization that we have done with the MSE loss, right? So you can see, if you look, I mean, these are not very big images, but you can see that it's mostly done a good job of reproducing the reference image, but you can see a little bit of artifacts right in the elbow. You can see a little bit more noise here, a little bit of noise in the hand. This area is fuzzy, but it's done a pretty decent job of converting what we started with, which is this image, into the content image that we want here, right? So one of the things we could do is, it'd be great if we could see the images along the way. That is, we can see as we applied a number of optimization steps, can we see how the image gets converted from pure noise to the content image that we want, right? So that's just viewing the progress. So we say after fit, after batch, append to certain images, and then after fit, show the images. So we capture the result of the optimization after every so many steps, and then we display it. That's all the image log callback does. And then we rerun the model so that it will now, after every 30 steps, it's going to display the result. So you can see you start off with noise. You're saying, hey, with an MSE loss function, try to optimize these pixels into pixels that look like this. So after about 30 steps, this is all you get. So you can see still that there's a lot of noise. Then it again goes to another 30 steps. Now it's managed to remove more noise. And 30 more steps, it gets here. 30 more steps, it got pretty close. And then another set of 30 steps, and we are here where this image is very close to the image that we are aiming to generate. Actually, you could try it, as I said, playing with it is good fun, and you can try different images and see how good or how poor a job the MSE loss function does in trying to get a noise image shape in the shape of the image to resemble the image itself. Okay, but that's, as I explained a couple of times already, is not our objective. Our objective is to apply the style of, let's say, a Van Gogh painting, Starry Night, onto this image, for example, right? So how do we do that? Because this was just a simple step to show, hey, we can modify the mini AI setup, or we can modify our data to fit into the mini AI setup in order to get to what we want. And one of the simple things he illustrated was how to use the mini AI framework by creating these dummy data loaders and then creating a couple of functions of threads, but without the reference label comparison, and then get from noise to an image. But that's not what we're after. What we're after is the transfer of Van Gogh's Starry Night style onto a reference image, as an example. So what we are now going to be discussing is a reference network, or a network called VGG that was used many years back in the creation or classification for image classification purposes. But over time, it's proved very handy or useful in grabbing or creating features from various layers of the image as we go through the classification process. So let's look at a VGG network. A VGG network image is something like this. It starts off with a 224 by 224 by 3 channels, converts it to 24 by 64, and then it begins to reduce the size of the image, goes to 112 by 112, 56, 28, 14, 7. And then here is something that is different than what we have so far done with our ResNet. If we have been following us along our journey, is here typically, as you saw a couple of lectures back in our ResNet implementation, what we did with this was to take, once we went from 7 by 7 to 4 by 4 and then to 2 by 2, we took the max pool and then eventually flattened the result. But what VGG does, on the other hand, is it takes this 7 by 7 by 512 image and directly flattens it to a 1 by 1 by 4K. So you can do the math and figure out that this 4K 96 is the result, same as this. And the reason, as he explains, as Jamie explains, that this network is not used directly and has been subsumed or replaced by ResNet and so on, is because if you consider the step after this flattening, we go from 1K by 1K by 4096 to, if we are doing an ImageNet classification, ImageNet has 1,000 classes. So we go from flattened 1 by 1 by 4K to 1 by 1 by 1,000. So by now you should be able to recognize that this particular fully connected to fully connected network is going to be is going to need a humongous matrix, because the size of the matrix that will be used to convert from here to here is 4K by 1,000. So that's a very dense and a significantly large matrix. That's one of the reasons that in modern networks, we don't do the flattening the way that VGG used to do it. But the purposes for which we are using VGG in this notebook and in general in all style transfer applications is not to worry about these, because we are not going to be using it to classify our image. We're just going to be using intermediate layers and the values that the intermediate layers have captured from our style image and be using those values. So we don't worry so much about the head, which converts this image into the various classes that we care about, right? So that's what is talked about here. He just uses from TIM what are all the VGG models. And then if we just capture the features from the VGG model rather than the traditional just VGG 16 models, then what we will get is everything except this head which is used primarily for classification, and that's not something we need. What we are trying to do is get a representation of this image in the intermediate layers of along the way towards classification. We don't care about these eventual flattened values. We do care about some intermediate steps and what the activations are during those steps. And if so, by creating VGG16 to be the features, we can then print out VGG16 and see what they are. This is the sequential network, and you can see that eventually it's just a maxpool 2D, and what we'll be using are some of these intermediate layers. But the important thing here is to notice what's the layer numbering, so that when we say 8, layer 8 or layer 9 or layer 10, we know which layer we are referring to, right? Now, he then goes on to say, so far in Fashion MNIST, we have just used the single channel images, right? So when we normalize, for example, it was a simple task. We just use the mean and the standard deviation for that one single channel. But now we have 3 channels. So for each of the channels, there would be a mean, right? So hence the 3 values of the means, that is for channel 0, channel 1, and channel 2. So R mean, G mean, and blue mean, and R STD, G STD, and B STD, right? So these are these values. Now, if we try to subtract the mean from the content image, that won't work. And divide by the standard deviation. This is like a naive, let's just take the mean, subtract it from our image, and divide by the standard deviation. That's kind of what we are after, but this is just an illustration to show that when the dimensions are different, then we can't just naively apply it and assume it will work. And the reason for it obviously is the image mean is a 3 shape. On the other hand, content image shape is 3 by 256 by 256. Now, if you know the broadcasting rules, as we have discussed before, this comparison and or application of subtracting the mean from the content image will not work, because it will start with the last values, compare it, say, hey, I can't broadcast this 3 value onto 256. As we know, it has to be 1 for it to be able to broadcast. So the simplest way, there are a couple of different ways that you can convert the mean into have a 1 and a 1 along the height and the width axis. This standard way to do it that he uses is introduce the 2 axes as none and none. The other way you can do this is also to use unsqueeze, which will create the 2 axes towards the end. So once we've done that and reshape this 3 to be a 3 by 1 by 1, then, which is what is illustrated here, once we do ImageNet mean this way, now we have 3, 1, 1. Once we do that, we can just do the normalization of the image by taking the tensor, creating it none, none, moving it onto the device, moving it onto this both the mean and the STD after reshaping them. And then we can use this exact same thing we had attempted to do here. And now broadcasting works in our favor, right? It will broadcast these values along the height and the width axis, and then do the subtraction and the division. So this is just an illustration that we need to be aware of how we are doing normalization and so on. It was simpler with Fashion MNIST, and it's also keeping with the spirit of what we have done so far. We need to have the code for anything we use. And so he has created the code for normalize. So that's, we can then figure out what is the mean for the content image after it has been normalized. And we can figure out after normalization, what's the min and the max values, right? And what is the mean if we take it along all 3 axes? This is just to compare. once we have implemented the code ourselves, then as is typical for what we have done so far, we can just use the transform.normalize. So all this code here is just to illustrate what happens in transforms.normalize. It actually takes the values, reshapes them, then applies to our content image that we supply to it. But keeping with the spirit of what understanding what every piece of code does and being able to code it ourselves, that's what these steps are all about. So now that we have coded it ourselves, we can just use the standard transforms.normalize function, and we check to illustrate that it has produced the same values as what we have done ourselves, right? So now, as we are on to the second journey of making or applying or transferring the style of, let's say, the mango image, Starry Nights, onto our content image, right? So what we want to do here is we want to take the content of some of the intermediate activations from the VGT layers. So we'll be taking some content of the result of applying the VGG network, taking some activations at some couple of intermediate points of this image. Okay. Now, we have already seen in a previous notebook how this can be done with hooks. So that will be one of our homeworks that if you choose, you can implement with hooks. But here he does it simpler. He just grabs the values directly. So that's what is done in the calculating features function. So if you're passed image, and if you're passed a set of or a tuple of target layers. So here we are using target layer 18 and 25 from our VGG network. So the layer activations for layer 18 and for layer 25 are going to be captured. Now, as I said, you could also, as a homework, implement using hooks. Here, he just does the capturing through a list, right? So what he does is he first normalize the image, pass in the image, normalize it, create a features list, and then with an index and a layer in VGG 16 max target layers plus 1. So that means we would grab the index, which would be, you know, the layer index, and the layer itself, which would be, when we say a layer, we are looking at the activation. So we, or I should say the actual layer, and then apply the X, which is the normalized image, is sent into that layer, up to that layer, and the output is captured as X. So if the I is in target layers, right, then you append to this list the copy of the result of the activation until that layer and put it into features. So this is just his way of doing what we have seen in the past as using hooks that we have done ourselves. So it'd be an interesting exercise to kind of change this code and use a hooks callback, for example. But in this case, let's just stick with this simpler example. And then here he says, let's just test it out to see whether by doing this, and we are looking at layers 18 and 25, whether we have captured by sending in the content image. So you do features as calculate features and then send in the content image. And then all we are doing is printing the shape to see, are we looking at some images that are of the correct shape. And so we see that the shape, it will calculate, and it takes a while because it obviously has to go through the network. And then it says, okay, what we have done by grabbing the layers 18 and 25 is the sizes of H and W at that time are 32 by 32, and this is 512 channels. Remember, there's no batch size here. There's just a single image. So this is the first part is just channels by height by width, and this is channels by height by width. So the two places where we have captured in 18 and 25 are the 32 by 32 size and 16 by 16 size. Right? So we have captured it in the 32 by 32, which is somewhere before this 28 by 28, and then 16 by 16, which is before this 14 by 14. That's kind of where we have captured the activations from the image. So what's the point of capturing the activations from intermediate layers? Now, if and this is where a little bit of the history or part one of the course may come in handy if you have looked at it, but if you haven't, you can spend some time to quickly catch up by reading this blog post. There was an earlier paper by, I think it was Ferguson and Briggs or something, I forget the name, but this is as good as any. What this particular blog post captures is what happens to an image as it passes through something akin to a VGG network. Essentially, what it happens to the activations as we apply a series of convolutions. So initially, in the early stages, the convolutional network captures the various styles or lines of different shapes. So these is one potential thing that it captures. This might be another. Vertical lines of this nature, diagonal going the other way, this particular shape, and these. So it's essentially in the early stages, it captures edges. As we go through further into the network, what it begins to capture are textures. So these textures, if you see, are made up of edges, but they are not edges themselves. They are a little more complicated than edges. These are the various textures that it begins to capture. You go further deeper into the network, and it is begin to capture patterns. So patterns have more than edges. Patterns have a repetition, and patterns use both textures and layers as part of them. So you can see that as we go deeper into the network, it begins to capture more of, in general terms, what is referred to as the semantics, which means that kind of the hidden meaning behind some of the things that's observed in the image. The earlier layers capture very simple things like curves, edges, and so on. As you go deeper into the network, you see that it's capturing, quote unquote, deeper or more semantic, more meaningful details of the image. And then after patterns becomes parts, so you can see that portions of the image are beginning to be captured here. And then finally, you might begin to see structures like eyes and wheels and things of that nature. So these become the objects which are then composed into the image. So that's, you can read about it. It's a great post. But why are we capturing different layers? We're capturing the textures or edges or patterns or objects depending upon which layers we choose to use as our reference layers, right? In this case, we have chosen layers 18 and 25. So I would say we are probably further deeper into the network. So we're getting a little more of semantics of the layers that we are capturing. So back to the original notebook. So that's the purpose of capturing a couple of layers from our style image. And how do we use that? Okay, so here, so far we have seen that we wanted to go from noise to reference or content image. All we used was the MSC loss. But now we are going to change the loss or add to the loss, and we are going to use what is called a content loss. So what we are going to do is add the comparison of the features from the style image that we have captured and compare it. As we optimize the image, we want the content image features to be comparable to the style image features that we have captured, right? And So we want to compare the features from the two later layers with those of the target image. So if our theory is correct, right, that by doing this comparison, we'll make sure that as we convert the image, we not only use an MSE loss, but we also compare intermediate layers and we say, hey, get close to this intermediate layer or the semantics of what this intermediate layer provides. Then we should see the structure of the target emerge from the noise without seeing a perfect reproduction of the target, right? So that's the thinking behind comparing the activations of intermediate layers between the style image and the content image. So that's kind of what we do. Now, the explanation here is obviously initially it just takes random noise, but over time, as the optimization proceeds, it will obviously take whatever is, and we saw this when we generated the image, right? Like after every 30 steps as we display, as the image begins to form, it will now begin to compare to the style image. So this call function just compares the input image and the target layers and compares it to the target features. So that's kind of the implementation of what I've been talking about in theory, where the target layers features are captured in self-target features. That's done through this function. And we obviously do it with dot.nograd because we do not want to take the gradient. We just want to capture the activation, right? So there is no gradient involved. And then here we just say, take the difference, square it, and take the mean. For each of the two layers, this is hard coded to just be 2 because we have just captured 2 layers and just is an illustration at this point, right? One of the things we don't do in this, and we'll see that because of that there could be some issues, is the resulting stuff. We are kind of comparing the activations of the intermediate layers of the target image and the content image that we're producing as we optimize it, but we're not bounding it in any way. That is, if for any reason by these comparisons, our values of the pixels go off the range of what we would like it to be, we are not constraining it in any way. So it may be that he says, instead of just doing that, we could potentially do some constraining of the values, and that might give us a little better result than before. And then we apply the loss function and train it as we have always done. And we also kind of take a log at every 30 steps. And what we see is you can begin to see the shape, if you will, right, of the content image. But obviously, there is, so far, again, we haven't actually done anything with respect to style. This just says, take the activation, send the activation, which is the noise, through the VGT network and capture it at layer 18 and 25, and also use that to compare it to the reference image and see how or what's the result. And we haven't used any MSE loss at all. We are just saying, do the comparison at these two layers and give you the result. And you can see that vaguely the shape of the lady with the glasses, you can begin to see it here, but you know, it's obviously nowhere near just using the MSE loss. But what this does tell you is that depending on the layers that you're capturing, and in this case, the layers we have captured is 18 and 25. And as I just went through the explanation with the blog, and you can read the blog in detail to understand what I'm saying in a lot more finer granularity, you can understand that 18 and 25, the deeper you go in the network, the more the structure of the network becomes important, that is the semantics, and not so much the edges and the, what was the second thing they talked about in the features, edges and textures and patterns. Instead, you would kind of begin to see the structure of the objects, such as the legs of people and the eyes of people and things like that, if there are such things in your image. So that's kind of what it's capturing is the structure, the eyes, the arms, the body shape of the lady, and so on. So instead, if we said to the network, okay, I don't want you to capture 18 and 25, let's worry about edges and early stages of the network. So, the edges and the patterns. That's what I want you to focus on. Let's kind of choose those layers and see what the result looks like. Then you can see that in this case, where we don't pay as much attention to the semantics, but we begin to pay attention to the edges and the shape, you can see that the result that's produced is a little more close to what we would want the eventual output image to be. And of course, you would get a lot better, I imagine, if you again combined the MSE loss along with the what is called the perceptual loss. So this content loss is also called perceptual loss. But if you want to kind of combine with this loss, the MSE loss as well, then I'm sure you could get even better results, right? So this is just with the perceptual loss, you get an image like that. Whereas with just an MSE, we saw what that resulted in. Now, the thing though to understand, and we discuss an even better technique to transfer style from the style image. Finally, we are down to what we want to do, which is once we understand that capturing some features of an image through a network such as VGG, and then as we train, making sure that our target image features resemble or are close to certain layers of our style image activations, and make sure that somewhere along the line of our target image, we choose the layers that we want our target image to resemble of our style image, then we are likely to get a transfer of the style. But the thing to keep in mind though is we don't want the structure of the Van Gogh image, for example, to be transferred. We want just the style, right? So what does capturing the style of our style image look like? Or what does it even mean to capture the style? Well, the capturing style means if we look at a style transfer, then what we want to do is we just focus on, let's say, this particular guy. If we want to focus on the style image, we want something of the nature of this image to be transferred on to the picture of Neil deGrasse Tyson, right? So what we don't care about is the location of what of the things in this image. We want to capture not the location, but something different than the location, which is indicative of what we refer to as style. Now, how do we do that? That's what this whole discussion around style loss with gram matrix is about. So we know how to extract feature maps. The feature maps are just the activation, right? But we want to capture the style, as I said. The style is something that's independent of the location in the image, right? So the style, as we've seen, is a little more oriented towards capturing the features, the edges and the patterns and things like that, rather than the semantic, which is the meaning of the object. So and the kinds of textural features, right? Now, we can't just compare the feature maps from the early layers. Why? Because along with the feature maps come the sizes, the height and the width, which means the location. But the location is not something we care about. We only care about location independent features of the style, such as the Van Gogh Starry Night, right? So how do we do that part of it? So we need a way to measure the style features that are present, right? And the style features that are present, and which one of the ways to judge a style is to imagine what things in the image go together without worrying about where in the picture they are. So you just want to see, hey, does the color blue go with the color green, and does the smattering or this is where the style, that means features of the image, independent of the location of the image. That's what we want to capture from the style that we want to transfer from. So the Van Gogh Starry Night, what we want to capture is not the location from the Starry Night, but the style from the Starry Night. So that's how we do that, is through this concept called the gram matrix. So let's understand the gram matrix. And I think if you read any papers and stuff, the concept is not as clearly explained. There's a beautiful explanation of the concept of a gram matrix. I think I haven't seen such a good explanation elsewhere. It becomes very intuitive and very clear if we grasp this. So let's consider a very small feature map. Let's not worry about 2 by 2. Let's just consider a 3 by 3, and then let's consider in each of these locations, let's say, a couple of colors, just to simplify the whole process and understand conceptually what's going on. So we have a red and a blue color in this location of 9 locations, and of a 3 by 3 H by W value. Then the next location has yellow and green, the one after that has a red and a blue, and so on. So if we flatten this 3 by 3, we'll get a 9, right? So each location is flattened. So this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what is laid out here. So you can see in the first location, so H by W, we multiply H by W, flatten it, and then we say in each location, what are the colors? There are 4 colors: red, blue, green, and yellow. And the 1 indicates the presence and 0 indicates the absence of that color in that location. So a red and a blue in the first location, so you can see a red and a blue, a 1, 1. The next one is a yellow and a green, so you'll see a yellow and a green and a 0, 0 here, and so on and so forth, right? So this is H by W on this side, and this is the features, quote unquote, right? That's the colors in this case, but it could be something else in the general case. Now, what we do is we do a dot product of itself, of each row with itself. So we convert an F by flattened H by W into an F by F matrix. And this F by F matrix becomes what is referred to as the gram matrix. And you can see that the gram matrix now captures certain qualities about this portion of the image that we would want. And what does it capture? It says, so what is illustrated when we do this, row by row dot product multiplication of the gram matrix, or this F by flattened H by W matrix. What it indicates, for example, is the yellow is at 5 locations, right? You can just horizontally add up, and there are 5, 1, 2, 3, 4, and 5. Now, how often does yellow appear with blue? Well, you can count the yellows and where there is a 1 and see whether there is a corresponding 1. Well, there isn't on this one, there is in this one. So there is 1 yellow with a blue, and here is yellow with a blue, none of blues. So you can see that the yellow blue is 3, and you can go on and fill in this matrix accordingly. So the F by F matrix is generated by using this kind of an approach and captures the correlation of, in this case, he has used colors to indicate features, but you can conceptually think of it as any other feature that actually occurs in the image, right? So why is this useful? It indicates the co-occurrence of features, that is, the features which are next to each other, or features which happen, I used the wrong term, it's not next to each other because we are wanting to decide regardless of location. So it's more, when do features co-occur, right? Not the location in which they co-occur. How often do they co-occur is what we are trying to capture through the gram matrix. So the important feature of the gram matrix is it indicates which features co-occur, how often, And additionally, it has no spatial dimension. So it doesn't matter where in the network or where in the image location they see. There is no H or W. It's just features by features. That's exactly what we want, right? How often does, in this case, yellow occur with green, with blue, regardless of location? Now, somehow the colors are used to illustrate the idea, but don't get confused. It doesn't actually just capture the color co-occurrence. That's not what is meant by this illustration. These colors are just stand-in for features. So it is the co-occurrence of features in the style we have chosen that the gram matrix is going to capture. And once we capture it, we can then use that in our attempt to transfer the style onto our content image. So let's look at the operations in code. So this is just the code for our, exactly the color features that we have kind of chosen to illustrate. And then if we just do an INSOM, and we have again discussed INSOM in the past, but FS, which is the F, and we call S to be the product of H and W. And so from FS, and then another will be GS, and then we want to go to FG. And the reason for using F and G, by the way, is as you'll eventually see, is you can't use the same term twice in an INSOM or in an INOP. So that's the reason for using F and G, but actually F and G are both features. This can't be FF in an INSOM notation. That's the reason we choose G. Then you just get, as a result of doing this matrix multiplication with it, or a dot product of each row with itself, and then with every other row, you then get this result. Of course, we could also do it simply by doing T dot mantmul with T transpose. That's essentially what we are doing. That's the process we have described, and that result is also the same. So now let's take a style image. We are now on to the final journey of applying the transfer or transferring the style from one image to the other. We're going to apply the cobweb style of image. So we want to take the style concept of the cobweb and apply it to the lady with the glasses that we saw earlier. So we take the style image, download it, and then we do the exact same gram matrix calculation, right? And we do this division is done in order to scale and keep the gram matrix scale in context. And by scale is meant, remember, even when we did this simple thing, depending on how often things co-occurred, like for example, yellow with yellow, there were 3 and 5. So there, when we flattened it, we got 5 instances. Now you can see that in a 256 by 256 image, if this feature were to apply a large number of times, it would go to the extent of, if it had happened in every single pixel, it'd be 256 twice. So we we want it all normalized. So we kind of divide by the height and width of the image, so that if we apply the style, but from a differently sized image, we still can capture the essence of the style, if you will. So that's the reason we divide by the height and width here, which are the -2 and -1 shapes. And then here we just convert, INSOM CHW. As I mentioned before, when we want it, it just can't be CC. So we say CHW, DHW, and then we convert it to CB and we provide the image. So what we do here is we take a number of layers, 1, 6, 11, 18, and 25. So we've captured 5 different layers and calculate the gram matrix for each of these layers. The other thing, and this will become relevant in the next notebook that we see, is in this particular case, we don't have any batch, right? This is just a single style image. that's being applied, if you will, to the single content image. So we don't have a batch dimension, but if one were to exist, then it will be BCHW and a BDHW to a B, C, and D, right? The batch dimension doesn't change. It's just that we flatten the last two HW and we convert the gram matrix to be just a CD. So if the batch dimension were to show up, it will be in the front and it will remain so. So that's the gram matrix calculation for a number of layers. So what we have done here is calculated the gram matrix for each one of these layers, because we want the style, if you will, or the features, sorry, if you will, captured from layer 1, from layer 6, layer 11, layer 18, and layer 25 to be captured by doing this calculation. And then we apply the style grams, or we capture it in style grams, the calculated gram matrix, and from the style image. The style image is this image that we have given. And then we look at the shape of the sizes, and it's at all these different sizes that we have captured the gram matrices of 64 by 64, 128, 256, 512, 512. Right? And you can also, here he just illustrates that you can also, instead of doing this, you can also use @got, which is just a attribute getter for style grams. Again, just illustrate the sizes. So now we take in a target image, which is this spiderweb image, which is our style. We calculate gram matrices for that, and we get an input and calculate the gram matrices for that, and do the mean square differences between the gram matrices of the 5 chosen layers. So we've chosen 5 layers, right? These 5 layers. And what we are doing now is we are computing the gram matrices of the style image, which is the features. Remember, the gram matrices capture the essence of the features. And we capture the gram matrices of the target image, the image that we are beginning to modify. And we compare the 2 gram matrices at each of the 5 layers. And we say, hey, I want to create a loss which compares the gram matrices at 5 different points for the style image and for the target image, that is the content image as it gets modified, right? And that we refer to as a style loss, right? So what we have done is we supply a target image and the target layers, right? And then store all the attributes, and without taking any gradients, the target grams are calculated with target image and target layers. And then all we do with the call is again F1 and F2 of the same thing as we have done before. So this just says for each of these layers, compare the gram matrix of the target image with the pre-computed gram matrices of the style image and make them close to each other, right? So we define a style loss to target and provide in the style image, and we compute the style loss of the content image. Obviously, it's a high style loss. It implies that the content image does not look like anything in the style image, right? In features for the chosen layer. Now we combine the 2 losses. We combine the style loss, and we also use the content loss that we have defined previously. And by combining the losses and then doing the training, we will now begin to see what a style transfer looks like. So you can see, and again, this is just captured as we go through the optimization process, and you can see the wonderful result of applying this style, if you will, to the original image of the lady with her glasses with some neon kind of background. I think this in the right was her original image. If you want, you can, here is the original image, and we can go all the way down to see what the that we applied looks like. And you can see that it's successfully transferred the style and done a very good job of it. You can see how the cobwebs have been shaped, how the cobwebs are hanging around her hair. This is the shape of her hair and they seem to hang neatly. On the other hand, it's there on the face, but not so much on some of the features like the forehead and stuff, which are still clear. So it's kind of done a pretty remarkable job of transferring the style. And of course, you can, take this and apply this Van Gogh Starry Night kind of image. So you just in that case, all you need to do is make the style image instead of the cobwebs. You can make that the Van Gogh painting. And instead of this lady, you can take the Neil deGrasse Tyson picture and try it yourself and see the results that you get, right? And here we are just clipping the values to the 0 and 1 value, and this is the result that you get. So here are the various things to try. In content loss, we have kind of only included 18 and 25, so you could instead use earlier layers and use all 5 layers as we have done in case of the style image. Then you can start from a random image instead of a content image. We have started with the content image of the lady. Instead, you could go to a random noise image and start from style image and optimize towards the content. Change the scale of the 2 components. That is, when you add these 2 losses, it's not always the case that each loss value is in the same size, if you will. So you can scale them appropriately. And then, so you can play with variety of these things. So for example, if it's, let's say, style loss of 0.2 plus content loss, you combine that and you do that and you see whether you get a better result with that. The other thing he does is really quickly, he kind of says, if we weren't to use a mini AI version, how would you do this? And, this is all, if you will, a flattened code, so to speak. So you just take an image, you set the image required grad to true, then you say define the optimizer, you define style loss, content loss, combine loss, and then take 300 steps of this, right? Now, the important thing here is you'll get a result which is as good and not very different from what we have seen. The question really, though, as he asks, is what if we now wanted to modify this simple flattened structure to add the ability to show the image at every 30 steps? Then we have to go and add code in between here, making sure that we save all of the relevant portions. What if we wanted to modify, instead of starting with style loss, what if we wanted to incrementally change it as we've been doing? So the point is that there are some pros, and you will see this is the reason, among the reasons why, for example, so many libraries aren't used, or Fast AI for that matter, Mini AI may not be used in Kaggle and stuff, because typically the Kaggle computation focuses you on a single instance of what you're doing. But if you're conducting research, if you're playing with parameters, if you want to experiment with a lot of different things, then a framework such as Mini AI proves to be very handy. So that's kind of what, and you can kind of, figure it out yourself in which case to utilize something that's flat, that doesn't use a library like Mini AI, but in what cases is it useful to use a framework. But this illustrates one of the examples of using a Mini AI framework. Any questions before we move to the second application? So it also shows that the Mini AI, well, it's a very simple framework, can be applied to a variety of different kind of constructs. As you saw here, we were able to take the Mini AI framework and apply it to a situation for which it was quote unquote not designed to do. It was traditionally designed just to do traditional supervised learning, but in this case you could convert it, create a couple of data loaders which are pretty much only useful to set up the structure, but otherwise don't do anything, and then create a model where the pixels are treated as parameters, and then off you go and you can use the rest of the infrastructure as is. Right, now let's look at an even crazier application of something that John talks about. He doesn't implement the most fascinating part of it, but he implements kind of the rudimentary part of it. And that is the whole concept of neural cellular automata. So what is that? And while this notebook connects, set it up and then we'll discuss what he is attempting to do in this notebook. Okay, so cellular automata is, I don't know if you're familiar with, but there are various things where the fundamental idea is to use a very small entity and to apply some fixed rules to the entities and have them develop behavior. There's no coordination or central space or location from which the rules are determined. It's just a bunch of rules, fixed set of rules applied to a set of elements, and by allowing the elements to update themselves. So it's all very local, but the behavior that emerges is at the global level. So, you know, for those of you who are not familiar with it, Conway's Game of Life is one such cellular automata. There's a lot of examples also that you can see in Stephen Wolfram's writings of usage of cellular automata. But the concept is somewhat stimulated or heavily stimulated by biology, where, you know, things happen locally, but then there is no structured coordination, no structured global or organ-wide or organization-wide coordination, but you still see a significant amount of behavior emerge by applying the rules just locally, right? So you can kind of look at a variety of references for this, and there's a lot of literature about cellular automata, but this is using or combining the concept of neural networks along with cellular automata. So cellular automaton is just a discrete model, consists of a grid of cells, such as we saw here, a grid of cells that with local rules, right? And they can be in any number of one of a number of states, and all the cells, if you have a grid of 16 by 16, then all of the cells in the 16 by 16 grid or the 8 by 8 grid are all updated simultaneously with a set of rules that determine the next state of the cell, right? And each cell only looks locally at itself and its neighbors and updates itself. That's all it does. It doesn't check. So unlike, you know, much like the convolution, which is, you know, you just depend on local pixels, but when you stack convolution, you get this effect of obviously looking back through the layers of convolution at a larger and larger portion of the network. In this case, none of that happens. It's just a fact of looking at local neighbors and simultaneously updating all of the cells yourself, but simultaneous application of the same set of rules to every location in the grid, right? And the beautiful thing about the cellular automata is they model some very complex systems. They exhibit emergent behavior, that is, you know, behavior that you don't that you are not explicitly programming in from just the interaction of the individual cells, even though the rules are very simple, right? And we have, you know, there is a game of life where, depending on how many values or what are the values of the pixels surrounding you, you may die or live. So every state you determine whether some cell is alive or dead, depending on its own value and the value of its neighbors. And the thing we are trying to we are going to be trying to do here is use a very small, simple neural network instead of the static rules that get applied to every location in the network, So that's what we are going to try to do and see what that results in. So we create a very small neural network, which will have some learnable weights. But the goal of this exercise is to keep that network to be very small and keep the parameters to be very small. As we saw in the style transfer, some of the parameters we are capturing, such as for a 3 by 256 by 256 image, is fairly large. In this case, what we want to do is keep the parameters to be very, very few in number, right? Now, some of the additional things that may happen is because there are channels, the channels may be used to communicate with different neighbors. But what we initially start with some initial state of the network, apply our MLP, which is the small MLP with a very few number of parameters over some small number of steps, much like we have done in diffusion or much like we have done in style transfer optimization. We just apply a number of steps, look at or compare the output to our targets and calculate our loss. And if you run some number of steps and you do something like applying the neural network, remember that the neural network is applied locally. That is, each pixel in the image just looks at itself and updates it. So it doesn't have any coordination, any kind of a communication, if you will, with the rest of the pixels in the image. But you grow, and after some steps, if you compare, then it looks like our target image. But the problem with this kind of an approach, we saw even with, for example, style transfer, is once we have done and taken a number of steps, we can obviously make, as we saw, noise, starting with noise, but we can make it approach an image. Here is an example of the type of stuff. Here is again a blog that he refers to. So what from noise, we can make it kind of resemble any one of these. So we can make, as we've seen before, we can make an image resemble a butterfly. But the question is not, can the image resemble a butterfly? But the question is, can the butterfly once built, can it continue to remain a butterfly? That's kind of the more interesting step we are taking. And more fascinatingly, can the butterfly continue to remain a butterfly even when the cellular estimator that we are using only applies the neural network or fixed set of rules to every local pixel, and there is no global coordination going on to say retain the shape that you have learned. The fascinating part of this particular blog post, it describes how they achieve the goal of, even if you were, for example, to remove or play with eliminating the sky or eliminating a certain set of pixels. You can see this, what I'm doing on the screen is blowing away a set of pixels of the image, but it recreates itself and maintains the stability of the final image, which, if you think about it, and if you understand, the underlying way in which it is done is pretty remarkable, because there is nothing, quote unquote, no rule which says this is the form that you have, because the form could be different. It could be something like eye, for example, and there's nothing which says here's the shape of the eye that you are supposed to maintain. Every pixel only knows about itself and its neighbors, but the network is still able to maintain and regain its shape. Now, unfortunately, he says that you can modify the network, the thing we are going to implement, to resemble, to follow this paper, but this is not the paper that he actually ends up implementing. I'll stop sharing to just show you the paper that he does implement. Is this guy, which is called texture generation with neural cellular animata. So again, he uses, I think, one of these, I don't think it's a spider, he uses some other texture, but the idea is very similar. Use a very small network, such as this particular network that we see here, use a very small number of parameters, apply it locally to each of the pixels in the image, that is, learn the parameters that you need to apply to each of the pixels in the image, and duplicate the structure so that we are able to get a vision of the structure. And then if you want to improve on it, he hasn't shown the full implementation. If you want to implement the full paper, you can also kind of try and destroy, build up that resiliency that is talked about. You destroy some pixels and it will continue to regain the shape that, or the texture that it originally had. So that's the goal of what we are setting out to do here. Again, using the mini AI framework, right? And how do we maintain these structure that we gain? So we have kind of, if you again think about the style transfer that we now understand. So suppose we just apply an MSE loss and gain the lady with the glasses image, fine. But how do we ensure that the lady with the glasses remains the lady with the glasses, even if we eliminate some number of pixels? If we remove our glasses, if we remove our arm, if we remove some pixels in the image, how do we do that? So the solution that this particular paper, the texture paper, talks about is to have a pool of training examples, right? So the idea is in the style transfer, and in this case also, it's easy enough to gain the final image, like the eye that we saw or the texture that we'll be seeing in this case. It's easy enough to gain that. The harder part is regaining or retaining the structure, right? So how do we do that? The idea is that we sometimes start, instead of starting from the particular noise or a single starting point, we start from a random state and apply some number of updates, right? And we'll apply a loss function and we'll update the network. Then what we'll do is we'll take that final output, which is optimized version of some starting point, and drop it into the pool of images that we will be using, right? As the starting point for another round of training. So what we do is we randomly choose starting points, do a certain number of optimization, and throw the result back into the pool. By this, we have created a pool of random starting points and intermediate points of the images, right? So what this does is our network, as it trains, has seen a number of different random starting points and converge to the results that we want, which could be a butterfly or an eyesight, or in this case, a texture that we, or a picture of an eye, or in this case, a texture as we see. So just by this additional thing of throwing in the random starting points combined with output of intermediate stages dropped into the pool from which we start, we can make or achieve the goal of resiliency, right? So for example, if you want a lizard, you get to the lizard, you optimize from a random starting point to some point which may not yet resemble a lizard, close to it, and throw that into the starting, so that when we in the future start from some erased point, it is possible for the network to start from that point and get back to the lizard, because it has seen images which are somewhat close to these random intermediate images, right? So in effect, what we have done is, besides maintaining or attaining the final texture or lizard or whatever image object, we have added an additional constraint that even after many more steps, we like to retain the final output shape. Okay, so that's kind of what the additional constraint helps us do. So initially, the model might end up in various incorrect states, but that don't look anywhere like the starting point. But it learns to start from these points and get back to the lizard as well. So that enables us to get robustness besides the and therefore the ability to maintain the structure indefinitely. So we don't start, unfortunately, with that fascinating paper of growing the lizard, if you will. And you can destroy arms of the lizard and the tails of the lizard, and it grows them back, which is pretty fascinating if you think about it. But we're going to implement, kind of the matching to match texture, right? So we want to produce texture without worrying about the overall structure. We just want the style. This is something that you should be familiar with by now. So using our style transfer from our previous, which uses the gram matrix concept, will help us to kind of do what we want there. We do the same start of training. We're going to start from some random, and then after some number of steps, we'd like it to look like the target style image. It should be familiar by now. And then the styling of the texture itself, it comes to us for free, and we'll see how that is, right? Now, keep in mind that this is cellular automata, right? So unlike in the other instances, we're just going to have our input, look at our neighbors, and going to feed through our network, produce an output. And every cell is going to execute the same rule, right? That's the whole concept of a cellular automata. That is, at every point in the image, you apply the same set of rules. The rules in this case are captured by the neural network, right? And the thing we have to worry about is the edges. And in this case, he shows a very nifty trick of where you can just say, rotate the edges or circular initialization, and that will help us get the network to appropriately propagate through the edges of the cell, right? So otherwise, we'd be padding them at 0, but in this case, we have a padding mode called circular, right? So the neighbors of the top right know they need to combine with the bottom left, and this with this, and side with the side. So with this circular kind of an idea, when the padding mode is set to circular, we can really kind of get rid of this concern about what do we do with the pixels at the edges, and we don't do the zeroing, but instead you say pad it circular, which allows the network to learn to pad appropriately, right? So this is our kind of very basic neural cellular automata network. So again, in this case, we start with just the style image, and we have seen what we need to do for a style transfer. We know these things: normalization, calculating the features, calculating grams. The only thing we have added here is the previous notebook didn't have the batch, but I kind of explained it there already. So instead of these, in this case, BCHW, so B is added, and then it becomes BCD. So we flatten the H and W into S, and then BCF and F, and we transpose it or multiply, so we get BCD as the output, and we scale it using these values. And in this case, he even shows that the batch is dropped. And then we know what the style loss target is and stuff. So we set up a style loss with our target image, feeding the new image. In this case, there is a batch of images that we feed in, and we get back a loss. So what we're doing here is essentially setting up an evaluation so that after a certain number of steps, we obviously want our image to look like the, or we want to apply the top web style to our image. Then let's now, here is the creative part in this particular notebook is let's define the neural cellular automata model. So here it's a very small model. You could try, these are things to play with on the notebook. You could try to increase the number of channels, increase the number of hidden channels. We start with just 4. We make the number of hidden channels 8, and we create a grid shape that because we want to apply the rules, that is apply the NLP to every one of the grid locations, right? So we have created a grid 128. So we create dots or zeros of n. N, remember, is just the starting point. And number of channels is the 4. Size by size, which size is 128. So it's 128 by 128. That's the grids that we create. And then here's the interesting part. We create dedicated filters, right? So in this particular instance, we just pick 4 hard-coded filters. These are the filter values that we choose. And each of them is obviously 3. So you would see that it's 6 by 3 in each case. And there are 4 filters. So there's this filter, and we can kind of also plot to see what does each of our filters, each of these look like. So when we say filters 2, that will be this guy, right? So we plot the filters just to, oh, I haven't defined it. So we get this, and this is, the zeroth filter. That's just something you can see. There's just a 1 right here, right? So you can see this, and everything else is 0 around it. And then you see the last filter, or maybe it's this guy. This is filter 1, filter 0, and then you see the filter 3. And that has kind of a filter. So we then apply the filter to each of the input image channels, right? And then note the circular mode. So we just kind of apply, the padding mode is circular that we apply, right? So since we have 4 channels of filters, so and we have the 4 inputs, so we have 4 filters and 4 inputs, so we have 16 inputs. And we have these 16 inputs, we have 4 inputs and 4 filters, 16 inputs for every location of the 128 by 128 grid. And that is going to be the input to our little brain model. The brain model is just a neural network that we're creating, right? And we apply the per channel convolution of the filters to our input X, and we get the output. So we get the output to be, in this case, batch size is 1. Since we have 16 inputs, 4 by 4, that's 16, and then apply to every location in the filter. So how do we implement the neural network, right? That's the image that's shown in this picture. That's the linear. That's this particular NLP that we are trying to implement. And that's implemented very simply as follows. So the brain network is a sequential set of layers. We take a linear layer, we take the number of channels multiplied by 4, which is the number of inputs, convert it and make it go to the hidden channels. Then we take from the hidden, then we apply an activation with each value. Then we go from the hidden channels to the num channels, which is, the number of channels that we have originally, and we say biases false. So what we are going to do, though, is we are going to, much like we saw in the gram matrix, we're going to map the batch, the height, and the width, So the B, the height, and the width, that's the 0th, the 2nd, and the 3rd, 0, 2, 3, into 1 dimension. So combine them all into B, H, and W, so that the location doesn't matter. The B, H, and W, the batch of the images, and the H and W get combined into 1 value here, and then the channels get pushed to the 2nd. So since we have a batch of 1, it means that we have 1 times 128 by 128. If you look at this guy, this is the batch, channels, height, and width. What we do is combine the batch, the height, and the width into 1 and push the channels to the 2nd, or retain it in the 2nd, if you will. So we then have the first to be 1 by 128 by 128, the 2nd is 16, right? That's what happens when we flatten the model inputs. But the brain network itself is just a sequential set of, remember how small this is, or notice how small it is. It's just 2 linear layers going from number of channels to 4 to hidden, and then from hidden back to the number of channels with a ReLU in between, and we move the model to the device. Then we flatten the input by rearranging it in the way that I just talked about, and then we apply the brain network to the model inputs which are flattened, and then reshape it back into the shape that we want, the X shape, which will put it back into the into the appropriate grids that we desire, right? Now, so if you look at the parameters for the brain, the first takes it from 16 to 8. So it goes, the weights are obviously 8 by 16, and then the biases are 8. And the second one takes it from the 8 back to 4. So the weights are 4 by 8. Right? So you can see by this, and we can do the NumL as well, which is the number of elements. And if you do that, you'll see that the number of parameters are extraordinarily small, because this is just two very small linear channels and a ReLU in between. It's about 168 parameters. Now, the thing he says is this is not very fast because we are reshaping it back into the input and so on and so forth. But if you, and this is the interesting part, and I would encourage people to go through it in detail offline as well. But if you did the, you kind of work through it, you'll find that what we are doing here is essentially we could exactly emulate it by using convolutional kernels as well. And we can use a kernel size of 1 in a convolutional layer, and the convolutions are very efficient, right? So we just apply this convolution on every pixel and looking at the neighborhood and producing the output. So there is nothing of a global nature that's happening here. You just apply the convolution locally on every pixel and have that update that pixel. Right, so we change the brain network to be a convolutional layer with a number of channels by 4, ReLU, another 1 by 1 convolution going from hidden to num channel with a bias of false, with an output being. So that's essentially simply the convolutional layer. Everything else remains the same. Then look at, make sure. We're just saying, making sure that the values are the same, and you see the result. It's 1 by 4 by 120 by 128, and all he does then is to put the whole value into a simple CA class. But before we do that, there's a couple of different things. Once we turn it into a class, there are a couple of other things that he does, that he talks about. The first thing is, if you start with, these are things which are typically seen in biology as well, but especially in the context of cellular automata or anything where the local rules are applied. If you start with something that's already stable and you keep applying a set of rules, then there's no opportunity for divergence or variety, if you will, or diversity in your output. To prevent that, what we do, or to encourage diversity, what we do is we only randomly update 50% of the cells, right? So this also is inspired by biology in the sense that biologically, when we think of what happens to cells, sometimes depending on some thresholds, some cells might update, some cells might not. This results in a level of diversity in behavior of a network with respect to the local values. So some pixels might get updated, some pixels don't. Here we are choosing a 50% threshold, say, just update half of the cells with the rules, don't touch the remaining half. The other thing that's done is 2 RGB function to scale and shows the first 3 channels as an RGB image, because we are starting with an RGB image. And then a third thing which is done here is an option to zero out the weights of the second layer. And by now, you should be familiar with what the zeroing out the weights of the second layer is helping us do. It helps us start off with something that is more stable. We have seen this technique discussed even when we Jeremy talked about, the diffusion kind of an approach where he was applying some initialization. You can go back and look at the 17 notebook to see what I'm talking about. He applies some initialization, but as part of the initialization, he kind of normalizes stuff. Orthogonal normalization, but he also zeroes out the output of some cells in order to enable them to start predicting. And for example, in a residual network, you want the convolutional path to be predicting zeros initially so that it's kind of similar to the ID path, right? So that's kind of what we're doing by doing the zeroing out of the weights of the second layer. So these are the few other modifications that are done to this class. And then he says, let me just check what happens when I apply an update of 0.5 and specify the BH and W value, and then apply a 0.5 probability. So mask is generated depending on the update rate, and this determines whether an update is applied to the original input or not. The class is very similar. You just say there is this additional parameters to zero out the weights or not. Otherwise, just put it in a class, and in the forward, provide the update rate, which can be, in this case, set default to 5, X is the input, the per channel convolution of the input and the filters, then apply the neural network, grab the BCHW, update the mask, and then return the value along with updated mask. And then this is just the thing to convert it to RGB. And then use the same dummy data set thing as we did earlier, kind of apply the NCA progress callback as a callback. So after every batch, it's just computing the losses. And then in this case, preview the image after every 64 iteration, plot the losses, show the preview images, and update the graph. This is kind of along the lines of applying the neural network. And then similar to the diffusion process, we want to sample, right? We are setting up a pool of grids. So we have 256 examples. They all start out as uniform zeros. And every time we call predict, we pick some random samples. Occasionally, we reset the samples to the initial state, apply the model a certain number of times. So if, for example, we are applying the model 50 times, remember this is a small MLP model. But if we apply it 50 times, we are making a network, a neural network, which is 50D. Right? So this is something we have to be aware of. So because there'll be issues of gradient explosion and gradient collapse and stuff. And then once the outputs are there, put those final output back in the pool. This is in order to maintain that stability, and then store our prediction, right? And in the loss, we use the style loss, right? So does the image match the style of what we want? And the one other thing he does is gradient normalization. So what that is you go through and because of this thing about, applying the network 50 times and so on, there may be gradient collapse or explosion. So to kind of manage that, you run through the parameters and normalize them. So this is just a hack to bring the parameters in control after having gone through a large number of steps. So you do all that. So this is our sampling function that we apply. So pick some random sample, occasionally zero out some sample, all these things that I talked about here, and the code, apply the model a number of times. So nothing in the range, you apply these sample, you go through the model a particular number of times, update the pool, store the predictions, get the loss, add the penalty if the loss is out of bounds. This is something we also potentially could add to our style transfer. The thing you saw a comment earlier. So this is something else you can play with and potentially add this overflow loss to the style loss. And that's what is done here, along with a style loss scale. Go backward and this. So now let's just that, and then we fit. And here's the plot of the fit, and we begin to see early on there's nothing. There's just location grid, and you will see it beginning to assemble stuff. But while it runs, and then we can print out the final batch, and this is something I ran earlier, and you can begin to see that in an RGB image. Right? When you show the image, it is beginning to develop some textures and some patterns. And you can apply it a number of times to a random initial starting grid, and you begin to see how, as we apply it, it begins to learn what the texture is. But what is amazing about it is not so much, we have already seen style transfer and stuff, it is much more complicated, but the notable thing about this is it's only 168 parameters, and it's only applying the rule to every pixel by itself. But despite just applying a local rule where there isn't anything which says, look at other pixels elsewhere, every pixel is just updating its own value. Despite that, you can see it. Of course, there's the padding around circle, but despite it, you can see it picking up the texture that it learns. So that is the remarkable thing about the neural cellular automata example. That is completely a localized application, and you can see by about 300 or 400 iterations, it's beginning to learn that. Right? So it's kind of a fascinating example. Of course, implementing something like this neural cellular automata would be even more interesting or fascinating. And in fact, I think they provide kind of a detailed description of how best to do that, and they describe the paper by which they're and reproducing this in a Colab notebook is available. But obviously, they'll not be using the AI framework, so it will be interesting if you can take this, probably also start with the network that currently and modify it in order to get to that. Pretty much covers what we will do in this lecture. Any questions? Next week, we'll again be going back to improving the implementation of stable diffusion. The original paper we implemented was something called DDPM, or diffusion probabilistic modeling. The next paper we implement, the next two papers, there is one called DDIM, and then there is Keras. It's not Keras as in TensorFlow, but this is the author's name, Keras. And Jeremy kind of takes us through a journey of implementing the DDIM paper, followed by implementing the variations in the Keras paper, and we'll also learn about how to judge whether our MNIST models are better through some kind of an automatic means. So that will be what we'll be going through. Any questions? And we'll just let this vision and look at our final batch of images before we're done. Any comments or thoughts?
Yeah, this was interesting.
Yeah. Oh, the one other thing I wanted to point out, in case you're interested, is this other style image, but I'll post a link in. This is the earlier version of, a prior version where he's using obviously FastAI library to talk about image enhancement, which he will again get into in one of our future lectures of, I think, super resolution, and also style transfer.
Mhm.
So that's the
That's one of the lectures from.
Sorry?
That's one of the lectures from the part 1 of the course, right?
No, this is not part 1. This is part 2 of a previous version. This is also part 2, but part
Okay.
2 of, he has taught, I think, 3 different versions of the course, like one in 18, one in 20. This is actually the one he taught was part 2 of 20, following from, by 20, I mean 2020. But he has also taught a couple of these courses, by couple, I mean part 1 and part 2, in using FastAI version 1 one version, the earliest version uses FastAI version 1, and he has taught part 1 and part 2 of that. And then there is a version using FastAI part 2, which again he is taught with part 1 and part 2. And this is the part 2 of the second version that he taught. And the current part 2 is the third version that he's teaching, or the third revision that he's teaching. But obviously the difference between this one and the current one is he uses the mini AI because he wants to take us, and I find that frankly more useful and simple because mini AI doesn't have a lot of the details that FastAI buries in the code. I'm familiar with them, but it's still a pain to recall all of them if you're using it. So that I'll post a link to this, and if you're interested, you can kind of go through that as well. But be aware that that uses FastAI part 2. So while some of the ideas are similar, some of the ideas of what he does are very different. But the concepts and the intuition that he teaches, which to me is the best part of how Jeremy lectures, is the intuition he wants to develop. So you can see here what we are kind of where we ended up, and you can see the texture of our final batch. You can see the texture in the image. And then if you apply a number of times to a random initial start stage, every 100 steps, if you kind of want to plot, you can begin to see. And this is the amazing part, right? We have only 168 parameters, and we are able to reproduce the texture, which I think is pretty remarkable.
Yeah, that's pretty amazing.
Yeah, I mean, once we're done, I really want to go ahead and kind of implement this type of capability. And you can see how they show, even if you destroy a portion of the faces and stuff, how it kind of rebuilds itself. That I find to be really fascinating. They're taking off the front, it rebuilds. And with a simple thing like just put back some randomly trained intermediate stages, and that in turn helps the network to say, oh, I've seen something close to this before, so let me get back to where I need to go to, starting from that point, because it's not something that there's always some point in the topography that it's close enough to that it can get back to the final state. Look at how much of the image they destroy. I think that's just pretty fascinating, given the small number of parameters. I mean, they're just blowing up significant portions. Of course, the image sizes are small, but still. So anyway, that's it for today, and hope to see you all next week.
Thank you. Very cool.